and how climate change will alter the speed of this transition is critical for understanding future sea level rise. Our next speaker will discuss ice compaction in Antarctica and its importance in the changes to our planet's climate. So let's give a warm welcome to Brita Horlings.
Ice tells us many stories. We can look up into the mountains or down to Antarctica to listen to them. We can look at an entire continent of ice or just a thin piece of it. Some of these stories tell us what a place was like just moments ago, while others can tell us what the entire world was like hundreds of thousands of years ago. It was these stories that captured my attention at the age of 11. I grew up in Vancouver, Washington, a city close to many fantastic wonders, such as the Cascade volcanoes. So I spent many days hiking these iconic landscapes. I was drawn to the glaciers of the area, such as the Elliott Glacier on Mount Hood, the Nisqually Glacier on Mount Rainier, and the Emmons Glacier, also on Mount Rainier. I had read many articles talking about their rapid demise on timescales that shocked me. To think that some of these glaciers, by the end of the century, could be completely gone, with consequences to our water supply, our salmon population, our hydropower. But perhaps the consequence that struck me most was the fact that my grandchildren and your grandchildren and their great-grandchildren would see a landscape drastically different than today. So I knew thereafter that I needed to hear more. This snow and ice, these glaciers of both our home and around the world, are telling us stories. So I set out on a mission to study one of these stories, Antarctica. In fact, we call the ice that sits atop the continent the Antarctic Ice Sheet. And it's a formidable entity of ice. If we compared its ice thickness in terms of space needles, sometimes this animation takes a bit to process, that thickness would be equivalent to 13 space needles stacked atop one another. That's a lot of ice, and it's important to study for a number of reasons. Maybe some of you have already connected it to a lot of things that are going on today. Global warming, glaciers and ice melting in other parts of the world, and sea level rise. So temperatures warm, ice melts, and sea level rises. However, knowing exactly how much warming, ice loss, and sea level rise is happening and will happen is not that simple. So to understand part of this complexity, we can think about the Antarctic Ice Sheet, which is a major future contributor to sea level rise, and think about it in terms of your bank account. So snow falls on the surface of Antarctica, and that's a lot like your income or what you put into your account. Ice is lost on Antarctica, and when we talk about ice loss, we just talk about melt or breaking off and forming icebergs. So this ice loss is similar to your expenses or what you have to take out of your account. We also have to consider one of many other things, the time it takes snow to turn, or what we call compact, into ice. And this is similar to the time it takes your check or other form of income to get processed and your overall account balance to get updated. So to understand this processing time a bit better, we need to look at the details of the Antarctic Ice Sheet. So near the surface of the ice sheet, we have a snow layer. And this snow layer looks like this somewhat. So it consists of snowflakes that are rather intricately shaped. And because they're intricately shaped, they don't fit snugly next to one another. There are air pockets that exist in between them that are connected. If we look at the bottom of the Antarctic ice sheet, it's just ice, but it looks a lot different than that snow layer. In fact, it's because that ice has undergone a series of major changes since it was that snow that had originally fallen on the surface of the ice sheet. So we see here that the ice crystals are spherical or oblong, and those air pockets that were in between the snowflakes have now turned into these tiny air bubbles that are no longer connected to one another. So we can also designate a middle layer called the Fern Layer. And this layer is the transition between snow and ice, and it looks as such. So the pieces of fern, called fern grains, are not intricately shaped like in the snow layer, but they're not as nicely geometric as in the ice layer. And the area that exists in between these fern grains is not as large as those air pockets in between the snow, but they're not those tiny bubbles that are in the deep ice. And they're still connected to one another. So we can think about this transition as snow falling on the surface, gradually over years changing into fern, and over centuries turning into ice as it moves deeper and deeper in the Antarctic ice sheet. We call this transition Fern Compaction. And in fact, Fern Compaction consists of a sequence of events. So snowflakes fall on the surface of Antarctica, and over time they start to lose their intricate shape. And eventually they will become round grains, and these round grains will deform and fuse together to one another. And the air pockets that were surrounding them get smaller and smaller as the air gets squeezed out. And eventually they will become those tiny air bubbles that we see in the deep ice of Antarctica. So understanding fern compaction and how fern compaction works is really important because we measure how Antarctica is contributing to sea level rise based on how the surface of it changes over time. So we can measure the surface of Antarctica through a radar pulse. So this just uses a similar method to a police car measuring speeds of the oncoming vehicles. So this radar pulse bounces off the surface of Antarctica and detects where that surface is. If there's melt that happens, that surface gets lowered. And when we go back to measure using that radar pulse, we will detect a lowering of the surface. However, other things lower the surface other than melt. And in special circumstances, fern compaction can lower the surface too. So during fern compaction, the air gets squeezed out, and if there's not enough snow to replace the snow that turned into fern, that surface is going to lower. And so when we measure using that radar pulse, we will also detect a lowering of the surface. So we need to understand fern compaction and how fast it's occurring in order to disentangle these two things, fern compaction and melt. So the sequence of events that makes up fern compaction seems relatively straightforward, but it depends on one major thing, climate. And when we think about climate, we could just think about the temperature and the amount of snowfall a location gets that's averaged over a long period of time. And because climate depends on these two things, so does fern compaction. So for example, at a colder location, fern compaction happens slowly. And at a warmer location, fern compaction is going to happen more quickly. The amount of snowfall a location gets also affects the fern layer. So when there's not a lot of snow, that fern layer is going to be thin. And when there's a lot of snowfall, that fern layer is going to be thick. So it's good that we understand these relationships because of the fact that climate is not the same across Antarctica. It varies depending on where you are at. So for example, here's a temperature map, and we can see that the temperature along the coast is warmer, and as we move inland toward the interior part of the continent, it gets colder and colder. And we can see the same variation if we look at snowfall. So near the coast, it gets a lot of snowfall, and in the interior, it doesn't get that much snow. So in fact, we can compare these maps and see a relationship between them, that the coasts will receive a lot of snowfall and be warm, and in the interiors, it's going to be have less snowfall and be cold. So this picture is complicated by the fact that climate changes over time. Maybe some of you have seen online or heard on the news that the global average temperature has been increasing. However, this amount of increase really depends on where you are at. So for example, in the west part of Antarctica, studies suggest that the west part is warming much faster than the east part. So this pretty much emphasizes the fact that a location can warm much faster than another location over time. So these climate complexities make it difficult to estimate fern compaction and understand how it varies across Antarctica. And in addition, our measurements are not at every single place on Antarctica. This is just a map of some of those major measurements of the fern layer and fern compaction. There are some gaps. And in addition to this, a lot of our measurements are not continuous through time. So my colleagues and I are attempting to address part of this problem. We are taking more measurements of the fern layer and fern compaction and also taking more continuous measurements. So we've been measuring fern compaction at South Pole. So how we do this is we attach a steel ball to a string, and at the top of it we attach an instrument. We place this contraption down a hole in the snow and fern, and when fern compaction happens, air gets squeezed out and that layer gets compressed and compacted. And so the string gets shortened. And the instrument on top can tell us how much shortening happens. So these instruments, called strain meters, we can place at different depths in the fern layer to get a better idea of how fern compactioning is happening at different depths. And also we can surround these instruments with instruments that measure the climate. So instruments that measure the temperature, the snow height, so that just measures the snowfall at the location, and also an instrument that measures wind. So this gives us a good idea of the big picture behind fern compaction. However, that big picture is still a bit fuzzy. We need to understand those smaller details, look at that pixel size, in order to better understand fern compaction. So remember back, whoa. Sorry about that. All right, well, remember back to snowflakes fall on the surface, and eventually they will become rounder and rounder. And so what we can do is we can measure the size and shape of those grains and those air pockets and how they change in the fern layer. So we can do this by using a relatively old method in a new way. We can use what's called micro CT scanning, and it uses the same technique as hospital CT or CAT scans that image the brain. It just can see smaller things. So with this method, we can measure, 3D image a piece of fern and know the size and shape of those fern grains and also the size and shape of those air pockets. And we can use this method to image pieces of fern at different depths in the fern layer and thus understand how fern compaction is working in a smaller detail. So we're also hoping to do this at another site in the near future, a site called Taylor Dome. And Taylor Dome is unique in the fact that the snowfall varies considerably across the dome, but the temperature stays relatively the same. So this means that at one side of the dome, it gets very little snowfall, and at the other side, it gets a lot of snowfall. Actually, it gets 10 times as much snowfall. However, the temperature stays relatively the same. The fern layer varies considerably, though. When the fern layer at the site that has a lot of snowfall is much thicker than the fern layer at the site that doesn't get a lot of snowfall. So remember back to the fact that we usually see locations that are warm and get a lot of snowfall, or cold and that don't get a lot of snowfall. However, Taylor Dome offers a unique opportunity to measure fern compaction in a place where the snowfall varies considerably, but the temperature stays relatively the same. And so when we measure fern compaction across the dome, we can amount any differences to changes in the snowfall versus changes in the temperature. okay, wow, this seems to have solved our problem, right? We just have to take a bunch of measurements using our South Pole strain meter technique and the micro CT scanning, and we will understand fern compaction and how it varies better, and we'll have solved our part of the sea level rise problem, right? Well, it's actually not that simple, unfortunately. This is mainly because it takes a lot of time to not only upkeep and collect that data, but it takes a lot of time to get there. It's over 9,000 miles away. And in addition to this, getting there also takes a lot of funds. And it takes a lot of funds to use some of these instruments that measure really specific snow, fern, and ice things. And additionally, some places in Antarctica are too extreme to go to. So with winds of over 50 miles per hour, poor visibility, and a wind chill that makes it feel like negative 99 degrees Fahrenheit, it's pretty much impossible to take measurements and just to get out there. For example, this picture actually shows a person. So what my colleagues and I are doing is that we're using the technology that has been developed over the past 70 years, computers. And in particular, we're using computer models, which are just a way of representing a real-life situation using a collection of mathematical equations. So what we can do then is use the data that we have from our micro CT scans and our South Pole technique strain meters, and we can use this as the basis for our computer model. So our model will need some inputs, and it will need equations that describe fern compaction, and those equations will need numbers that we can adjust using our data. And these numbers are very important to accurately estimate the fern compaction. In addition to this, we will also need climate data because fern compaction depends on temperature and snowfall, which are climate. Our model can give us fern compaction in a couple of ways. So it can give us a curve that looks like the one in red. So it can tell us that at the very surface how much air in those air pockets in between those snowflakes there is, and how this amount of air decreases as you go deeper and deeper towards that ice layer, through the fern layer and to the ice layer. And we can also compare this with the data, which are the tiny blue dots there, to see how well we're estimating this fern compaction. We can also get something else out from our computer models, how fast this fern compaction is happening. So this is really powerful because we can not only use this computer model for the sites that we took measurements at, we can use it across the entire continent to measure fern compaction. And in this way, we can understand how fern compaction varies across Antarctica and better understand how Antarctica is contributing to sea level rise. So this may complete one part of the story that the ice in Antarctica is telling us. But the quest to predict and resolve future sea level rise is far from over. And my colleagues and I will continue to search and listen for more stories that the ice in Antarctica and elsewhere around the world is telling us. Thank you. Any questions? Yeah.
On the part point, just now you described both melting and fern compaction can result in the ice measurement deviation. So how can the professional researchers to find out which one actually caused the deviation?
Can you repeat the first part of your question?
Just now you described both melting, the ice melting and
yes.
the fern compaction can result in the deviation of the ice measurement.
Yeah.
So how can the professional researchers can make sure which one?
Yeah. So in estimating, of course I had to simplify it, but when we estimate how Antarctica is contributing to sea level rise, we have to use a model. And in this model, we will also model fern compaction. And so we need to understand fern compaction in order to get a better model for the fern compaction. And if and so that we could better understand how Antarctica is contributing to it. Does that make sense? Okay.
Thank you.
Any other questions? Yeah.
I think one thing that wasn't clear to me, maybe that's related to what he's talking about, is
Sure.
the stress gauges. Like, how does
Strain meters.
How does that actually work? Because I'm trying to figure out, what is that measuring actually? Are they sitting on the fern? Are they sitting on the snow?
So the top of the instrument will sit on the surface of the snow, and over time it will actually get buried under the new snow. And over time, that layer, that length of the hole, will start to shorten because the fern compaction is happening. And so the string will get shortened. And our instrument on top can measure how much shortening has occurred.
It's got to wait basically until it gets to the fern layer.
Yeah, well, yeah. So compaction is happening in the snow and the fern layer, yeah. Yeah. Okay, Ed.
How much melting is there in Antarctica?
So in Antarctica, actually, melting is not a big factor. In Greenland, it's a big factor, and that makes this picture a lot more complicated. So when you add melting in the fern, our fern model will get a lot more complicated because we have to add a lot of the heat processes associated with melting. Yeah.
So I have two questions. One is sort of technical and then one is sort of general.
Sure.
So the technical question I had was, what percentage of the devices that you all put out do you actually manage to reclaim data from, based on, like some being lost to those crazy conditions you're talking about? And then the second is, what percentage of Antarctica is actually mapped? So you said there's 13, space needles of ice over the surface. What percentage of the surface do we actually even know how deep the ice is?
So we, I think, actually have a good idea of the depth of the ice in Antarctica from, well, we use measurements, radar measurements, but also other measurements and models to predict that depth of the ice. So we actually have a pretty good idea of the depth of the ice. Now, what was your first question again?
How many of the devices that you put out there do you actually manage to get data out from?
I think actually a good percentage. So I personally have not been to Antarctica yet. I'm hoping to go in a couple of years. But my colleagues and I think, have recovered a lot of their instruments, and only several have failed. Yeah. So I can't give you like an actual percentage, but I think we can recover a lot of data, mostly because we don't go to those really extreme sites. Yeah. Yeah.
How do you take the samples for the CT scanning, and how do you transport them?
Yeah, so those samples are taken from fern cores, so just a cylinder of the snow and fern, and they're actually transported back to a lab. And people in Dartmouth are actually taking these measurements right now, and I think what they do is they cut out a little piece and put it in the scanner. So I think it's on the millimeter scale.
It doesn't melt?
Well, it has to be stored in the right conditions. Yeah. Yeah.
It sounds like this whole story has big impacts on us and our the lives that we'll lead in the near future. What would you say is the biggest hurdle to getting more data to better understand this?
So I think right now getting funding is a bit difficult. So I think that's probably a big limiting factor.
What do you specifically spend time each day working on?
So I mostly do the modeling, and so we have a lot of data, and right now I'm building a model that can better estimate fern compaction using more physics. Yeah. Yeah.
So, about measuring the fern and seeing actually what's going on with the melting and the raising and stuff like that. How much of an impact does this have on the breakage and stuff? Like the amount of fern versus the amount of ice when something calves off and falls off. Does that have any impact?
So I I don't think that this particular, if I'm understanding your question correctly, I don't think this particular process has very much impact on icebergs breaking off. Yeah.
Because the amount of fern might have an effect on the consistency that might affect breaking off.
That's true, yeah, but I guess we also have to think of the thickness of the ice. So the fern is just a couple hundred feet, if that, and well, Antarctica is 13 space needles thick, so a lot of it is just ice. Yeah.
I remember Karl Marx said one sentence. So the total wealth created during the industry revolution was even much more than the history before, and the bad ramification and the result was environmental deterioration. So how can we, ordinary people, can slow the ice melting like we do compost?
Well, I think obviously it's going to be a group effort, but I do believe that individual participation is important. So I guess, you know, monitoring carbon emissions, for example, or carbon dioxide emissions.
Really can affect the ice melting.
What was that?
The human daily life can really affect the ice melting.
So yeah, our human influence.
I mean, besides the industry, you know, product, like our human life.
Oh, so like everyday.
Yeah, yeah.
I think that even that has some effect, but obviously I think industries or something like that, and yeah, controls on that are going to be difficult.
Can an environmental studies major maybe answer a little bit of that?
Go ahead, yeah.
So, okay, I mean, industry's a big deal, but like thinking about your personal carbon footprint includes like how do you drive, how do you get around, what do you eat, which sounds nuts, but like meat, for example, especially red meat, is pretty resource intensive.